peak where it kind of says that little lambda max and then it says T3 really close to it. At that peak, that would be mostly where you would see like a violet color. At the next, let's look at the one that says like T1. I think that's a good one, at T1. That's the very smallest peak. That's a little bit past the red color, so that's even like out of that visible spectrum. So we're not even going to be able to see a color there, but there's not very much intensity because we can't see it. At T2, that's probably where your red color would be, so there's a little bit of intensity. I want to think about what I mean here when we say intensity. And intensity just means like the amount of energy that's being emitted or the amount of energy that we're seeing. We talked about before that wavelength and frequency have an inverse relationship. So when we think about energy, we know that frequency has the same relationship as energy. So as frequency gets bigger, the energy also gets bigger. So as frequency increases, energy also increases. But wavelength does the opposite. As energy and frequency increase, the wavelength actually gets smaller. So violet light is closer to UV rays, and we know that UV rays is where the wavelength is getting smaller, and then after UV is X-ray, and we know those are even smaller, and after X-ray is gamma, and we know those are the smallest. So those, as we move from red to violet, we know that the wavelength is getting smaller, so we know the energy of those light waves have to be getting greater. So red light doesn't have as much energy as violet light does. So violet light will have the most energy, which means it's going to have the most intensity. And that should make sense because there's more energy within those wavelengths. There's more energy within that wave. So that's why we're seeing that there's a really tall peak where there's the violet visible light because there's just a lot of energy that's going on there. They hold a lot of energy compared to the red light. Okay, so again, if you have questions on this, I want you to write down some questions that you have because I know it's kind of hard to listen to it and just look at it instead of maybe seeing it as me talking about it at the same time. So if you have questions, write these down. On slide 3 still, it says that we kind of get into something that's called a black body. And we've talked about a black body a couple times before, but I wrote it up here that an ideal black body absorbs all incoming radiation and it will re-emit that radiation in some type of spectrum. So I have a black body, it's absorbing all this radiation, and it can also emit all of this radiation. An ideal black body is the same thing as like what we would call a perfect black body. And that just means that all of the light that hits a surface that we would call a black body can absorb all of that light. It's a perfect absorber, but it's not only an absorber of light, it's also a perfect emitter. So it can absorb light like no other can, and it also can emit light like no other object can. So ideal black body, it absorbs all light and it can also re-emit that light, okay? Okay, let's move on to slide number 4. And in this slide, it's titled the UV catastrophe. Now, let's talk about this first because we'll talk about all of these bullets, but UV catastrophe is pretty much something that really moved scientists from classical physics to starting modern physics. So this is a huge deal,